Thank you very much. That was a great introduction and lots of things to follow on. So please let me know if you don't hear me well. I'm going to share my screen in the meantime. And I will also try to monitor the chat. If there's any burning question, please raise your hand. Feel free, no worries at all. Right, so this, I'm going to time myself because timing is always the essence here. So this part is about evaluating machine learning models, and in this presentation, essentially, I would like to give you a little bit of introduction of the basic components that you would need to evaluate your machine learning models. So starting from the very beginning, I just want to tell you, let's put some terminology here to understand each other, but it's basics. If you're familiar with machine learning, essentially we have some domain objects where we extract some features, which is the relevant information we use in the model. We also call them the data. We have some tasks to solve. The output is the prediction generated by the model. And in addition to the model is essentially an instance of a learning algorithm. And the whole combination of learning algorithm and the instance, so the model, is the learning problem we try to solve. And depending on how this training data is performed, you can have supervised learning or unsupervised learning. For this talk, we'll focus on supervised learning without any actually loss of generalizability. So I have essentially two main objectives with this talk. The first one is to provide you some descriptions of the basic components that are required to carry out a machine learning experiment. And we will understand in a second what do I mean by that. And what I would like to provide you is an overview of the basic components, not just recipes. So just like to understand the very, very basics. And the second goal is to give you some appreciation of the importance of choosing measurement in the appropriate way. In other words, sometimes just measuring the accuracy, which seems to be the most used metric, may not be a good idea, may not be the right measure to use. It's not always the case, and we'll see. We'll try to understand what's the point there. So, in explaining a bit of machine learning experiment, we have to deal with different elements here. We have the research question, which is what we're trying to achieve. We have the learning algorithm in particular. I try to play a little bit with the colors. So let me know if that's clear, or if not clear at all. Feel free to interrupt me. We have the learning algorithm, so we have the algorithm and the instance of those algorithms. So M going to be the models, and we have some data sets in general. Classical examples of research questions might be: how does model M perform on data from domain D, for example? Or a much other question actually could be how model M would also perform on data from a different domain. That's a completely different question to ask. Or, for example, which of these models, so we have different instances of the same algorithm, has the best performance on data from D? Or another kind of question might be, which of these learning algorithms gives the best model on data from D? All these questions are actually pretty standard question we tend up in asking ourselves when we set up our machine learning experiments. And if you're wondering, the difference between the last two questions essentially is like, how do I play with hyperparameters in order to understand which is the best distance of the learning algorithm I want to use on my data? And then the second and the last question, on the other hand, is which is the best model on my data? And there's an explanation for that in the very last slide about it, and the reason why we want to do that. So in order to set up our experimental framework, we need to investigate essentially two main questions. There's actually three, but in this talk, we're going to go for the main two. And the first is what we need to measure, first of all. And the second is how we measure it. The last question is actually how we do interpret the results. That would be the next step. We don't have the time to cover that, but in essence, in other words, the last question means how much your results are robust and reliable in order that you can trust them, even from a statistical point of view. So let's start with what to measure, and I want to start this with very basics. We're going to talk about the very where everything starts, which is the the so-called confusion matrix. And for those of you not familiar with this one, let me just introduce a little bit the basic components. This slide's going to be a little bit dense, but play with me a little bit and let me know if that's not clear at all. So the confusion matrix, we'll consider a binary classification problem also for the rest of the slides. So just with no lack of generalizability, but still to make things easier to understand, in my opinion. So we start with, in clockwise order, this matrix is actually composed by 4 different components. We have the true positive, which are essentially the positive samples correctly predicted as positive. We have 2 classes, so positive and negative in general. We have the false negative, which essentially are the samples which have been wrongly predicted as negative. They should have been positive. And the sum of those is the condition positive. So the total number of real positive samples we have in the positive class, the total number of samples we have in the positive class. The true negative is the negative samples correctly predicted as negative, and the false positive is the negative samples wrongly predicted as positive. So, and the sum of those is the condition of negative, or the total number of negative samples we have in our data set. The sum of everything in this matrix is T, so P plus N is the total number of samples we have in our data set. So these are the 4 essentially basic components on which lots and lots of different metrics are built upon and essentially derived from. So first of all, we have the portion of positive, so it's the ratio between P and T, and the portion of negative is the 1 minus pos, or the portion of N over T. So now things starts to get interesting, in my opinion. So we have the main primary metrics, and so all the other metrics we're going to talk about are essentially derived from these ones. We have the true positive rate, also known as sensitivity, also known as recall. For some reason in the literature, people over the years tend to call with different names the same thing. Essentially, recall or sensitivity depends on actually the context we're talking about. If it's, for example, machine learning or information retrieval, you might have different terminology, but they do refer to the same thing. It's actually the rate of true positive cases. So TP over P. I try to highlight in the matrix the squares we are considering every time. In the case of true negative rates, it's essentially true negative over N. And the confidence, also known as the precision from information retrieval, is the ratio between the true positive over the true positive plus the false positive. Now we get with the secondary metrics. So we're not going to cover all of them, or we're going just to cover 2/3 of them. And we're going to see the difference because one of the main points of this part is like, are those metrics really the same, or is it really always it doesn't really matter which metric we're going to choose? Or better worded, what's the difference between choosing one metric over the other? So a popular secondary metric, as also known as F1 score, is essentially the harmonic mean between precision and recall. Also known as the sensitivity over specificity, the confidence. The other and the super popular metric lots of people actually tend to use in their evaluation is the accuracy. And the accuracy, looking at the confusion matrix, is essentially the ratio between the good predictions. So the true positive plus the true negative over the sum of positive and negative. That's the accuracy, essentially. So at this point, well, there's also this one. Bear with me another minute. This is the very important metrics I want to introduce. It's on the spectrum of the less famous ones, but actually, in my opinion and to my experience, this is one of the most effective. So the Matthew correlation coefficients, MCC, is actually differently from other secondary metrics. It's still a secondary metrics. Different from all the other secondary metrics. It's considering all the possible components in the confusion matrix. So let's analyze the components of this formulation. Essentially, we have the good results, so the good predictions, minus the bad ones. And so the good, the bad, and the ugly ones is the ugly one is essentially all the possible combination of good and bad in the denominator. So that's the idea of matching correlation coefficient. So we're going to come back to that later, but that's the metric I want you to work with. So let's start by asking, is accuracy a good idea? So in general, when we have some data for evaluation, so that's the formulation of accuracy on top of the slide. So we have some data for evaluation as representative for any future data, right? So imagine we have some data that we want to use to evaluate a model. I haven't told you yet where this data come from. Imagine someone is giving you this data, which should be in general the case. Nonetheless, the model may need to operate in different operating contexts, and the different operating context might mean, for example, different class distribution. So if we do treat the accuracy on future data as a random variable, and bear with me, this is the only thing a little bit more technical I'm explaining in the slides, and we take the expectation as a random variable. So we assume in the same case, in the simple case, uniform probability distribution over the portion of positive. Essentially, we end up understanding that the accuracy, a better measure for this one is the average recall. What we call the average recall essentially is like true positive rate, the half of true positive rate plus the half of true negative rate. What this all means is that if we don't know what's going to be the future operating context, if we choose the accuracy, we're essentially assuming we're assuming that the data we're using to evaluate the model are going to be the same distribution of the data we're going to see in the future. So it's a huge assumption we're doing. If we don't know anything at all, maybe average recall is more, it's probably a better choice on this particular case if we don't know anything about the future distribution. So let me give you an example. Let's imagine we have the same data set, two different models. On the left-hand side, you have this confusion matrix. So we have 100 samples in total, 80 positive, 20 negative. The first model, M1, is actually producing the results you see in the confusion matrix. The accuracy on the first case is 0.8. The average recall on the other end is 0.88. If you go on the second, on the right-hand side, we have the second model on the same data, which is producing 85% of accuracy. So compared to M1 seems a little bit better. But if we have a look at the average recall, we have the 0.72. So if we just look at the accuracy, we might be we're leaning towards M2 on the data. But if we carefully look at the results, actually, it seems that M1 is doing a better job in predicting of the negative class. And this is one of the main issue we have with accuracy. We're just considering the positive classes. So the average recall is helping us in reaching this point and better understanding what's going on. So is accuracy a good idea? Probably not really in this particular case. Let's have a look with the F1 measure right now. So a recalling F1 measure is simply the harmonic mean between precision and recall. So on the right-hand side, in the left-hand side, we have model M2 performing on D. In this case, I'm going to tell you that we're going to switch the data set, not the model. So we fix the model right now. We change the data in this particular example. And what I want to show you here is like if we taking this results from this confusion matrix, the F1 is going to be 0.91. The accuracy is 0.85. It's the same results we got from the previous example. But if we move on a different data set like this one, instead of having 100 sample, we have 1000 sample. And in particular, we have lots of negatives that we didn't have in the previous example. The accuracy is going to go to the roof, 9.99, whereas the F1 measure is still staying on 0.91. It's essentially the same thing. So what's the lesson we can derive from this one? The thing is, F1 has to be preferred in domains where negative abounds, and most importantly, negative are not the relevant class we want to classify. And so the takeaway message from this example is accuracy, in the previous example, accuracy was essentially taking a look at just the correct predictions, but was not considering at all the negative classes. In this particular example here, we have lots of negatives, but negatives are not the interesting bits here. And in this particular classification problem, so we want to do better on the good ones, or sorry, on the positive ones. So if we have a look at just accuracy, well, actually, we definitely go with M2. But if we might say no, actually, 0.91 is the right measure. And I just want to clarify here what could be an interesting case on negatives here. So consider that precision recall F1 are all coming from information retrieval. Information retrieval, you're interested in the right results returned by a search engine, not the negative ones. So typically that's the case in which, for example, negative are not relevant at all. You're not interested in the wrong results. You're more interested in the right results you return from your search engine query. Okay, so what's the case in which this is not the case? So like we do want to account for all the possible classes. And so let's have a look at this example back again. It's again this particular confusion matrix. We have again 100 sample, and in this particular case we're doing a very corner case, but could be the case most of the time if we don't account for class distribution properly, which is this classifier M2 in this particular case is doing brilliant job in classifying the positive one, is doing terrible job in classifying the negative ones. So we have no negative at all predicted. So if we come to F1, we have 0.97, accuracy 0.95, MCC is undefined, and this means that there's something wrong here. We can't actually predict any performance because it's totally wrong. On the other hand, in this other case, we do a different, we do slightly better on the negative, but still there's still confusion on what's going on there, as in we are doing a good job on the positive, a decent job on the negative, but still we're missing some errors on the negative. If you do the counting here, still the F1 and the accuracy are over the roof, so they're very high. So you might be tempted to say, okay, my model is actually doing pretty well. But the thing is, we're doing wrong on the negative class, and the negative class counts in this particular case, and so the error on the negative must be weighed differently because it's the least represented class. And so the MCC is telling you, well, it's 0.14 is not going to go anywhere. I should probably mention that the MCC, different from the other metrics, is a metric which doesn't go from 0 to 1, goes from -1 to 1, and essentially you have to read this metric in this way. So -1 is completely, it means you're classifying the classes in a completely opposite way, so positive from the negative and the other way around. MCC of 0 means random prediction, and MCC of 1 means good prediction. So takeaway message from here: MCC to be preferred in general when predictions on all classes count. So takeaway lessons are essentially told you already. But the main takeaway message I want to convey here is when you do an experiment, don't just record accuracy. Instead, keep track of the main primary metrics, and the secondary metrics can be derived afterwards. Okay, so now the second question is how to measure things. We focused for the first part in the metrics side. Let's now focus on how we do prepare the data to do that. So in evaluating supervised learning models, in general machine learning models, the whole process might seem quite straightforward. You have to train the model and calculate how the model is doing on choosing the metric you want. You want to calculate how the model is performing. Well, actually, this is not the right way of doing it, because this would be an overly optimistic estimate, also known as in-sample error. What you want to do instead is your goal is not to evaluate the model on data you have right now, the training data. You want to evaluate your model on data the model has never seen before, or in other words, data the model will see in the future. So, and so that's technically called the out-of-sample error. So how do we do that? One simple and clerical way of doing it is the holdout evaluation. So you have your whole data set, You have the training set and the you split this into a partition. Partition means there's no overlap between samples in one set and the other set. You have the training set and the test set, also known as the holdout set. Important message here, and I'm going to repeat this quite often later today. The test set has to be put aside. So the test set is something you generate in the very beginning of your pipeline. So you start by saying, okay, this is my data. I want to take away some part which I will be using later. But the test set has to be taken outside, and you have to forget about it. So the test set has to be retaken back when you're doing the actual evaluation. From now on, when you have the test set, the training and the test set, you do everything on the training and the rest of it, and only the evaluation at the last step on the test set. So again, the test set is only for performance evaluation, nothing else. So to do that, we can simply split the train and test. It's a simple Python function. It can be a utility function from scikit-learn, train test split to do the job. And that's it. The problem is that this kind of a train test split works, but it's a sort of a weak way of evaluating performance because it's highly dependent on how you select the samples in a test partition. And remember, we're considering this test partition as representative for future data. So we're saying, okay, this is the data we want to evaluate a model, and this is going to be a good test because the model in the future are going to see data which resemble what I'm using right now in the test partition. So what could be a better way to do that? We can do a slightly more sophisticated partitioning process, which is called cross-validation. The idea is that we do generate several test partitions, and we use them to assess the model. So we have the data set, we randomly split the data into k partitions, also known as folds, and then we use this folds in turn. So for k times, we fit the model on the k-1 partition, the blue ones you see, and the pink one are essentially going to be used as evaluating partition, so the test partition or validation partition. And we repeat this process all the time. On k different models, this is the important bit to remember. All the time you have a brand new model you're training on a different partition, and then you average over the different fold. And so you have chosen the metric in the beginning, you can average the value of the metric over the different partition, and you have some indication of how the model is performing on different versions of training and test partition. Remember that the deal is always the same with the test data. Test folds must remain unseen on the model during the training. So once you generate the test partition, you have to use it only in the end to evaluate the model. Whichever feature selection, whichever processing you want to do, you have to do it only on the train test and then apply on the test set. K can be any number. There are different values in literature. K can be 5 or 10, or if K is equal to N, so the total number of samples, this is also known as leave one out cross-validation. Cross-validation can be repeated, which means you can change the seed and repeat this process multiple times, although you're increasingly violating the independent and uniform independent and what's the other one? Independent distribution. Identically, thank you very much. Identically and independent distribution of the sample you have. And cross-validation can be stratified. Which means you want to maintain the same class distribution among training and test folds. And when you have imbalanced data set, or if we expect a learning algorithm to be sensitive to class distribution. In scikit-learn, in fact, you have a long list of different methods you might choose to do the cross-validation, group k-fold, shuffle split, and many others. So you don't have to reinvent the wheel. And I want to just clarify in this last bit that there's a common mistakes in which sometimes you want to use cross-validation to do model selection, also known as hyperparameter selection. This is methodologically wrong, as parameter tuning should be part of the training. So test data shouldn't be used at all in parameter training, in hyperparameter tuning. What you can do actually is, like, you do your partition, so you generate your test set, then you forget about it, and then you take the training set, you split them in training and validation, and so you do your hyperparameter tuning on this new training set, and then you validate this values, or so this hyperparameter tuning on the validation set. And once you're done, you retrain everything on the full training set you had in the beginning, and then you validate. You assess the model performance on the test set. That's a methodologically sound way of doing hyperparameter tuning on the actual data. The last thing I want to mention here is the no free lunch theorem, and so the fact that it doesn't exist in this has been proven a long time ago, actually, that for some data the model working better, from some other data there are other models working better than the previous one. So it's essentially doesn't exist a unique model which can rule them all. So you have to try multiple times, as Jesper was saying before. Random forest is the baseline, and you don't have to use, you don't have to shoot with a cannon of deep learning, for example, if you just a linear model can do that. And so that's why you sometimes need cross-validation, because cross-validation provides you a robust framework to do this choice. So once you have your experimental framework set up, you can essentially change whichever module you want and repeat the same process and use cross-validation to see how these different models perform on different versions of test, train, and test, train and validation data set. So this is the link to the repository. In the interest of time, I think that I just want to show you the basic. Yes, I'm almost running out of time. So I just want to show you the basic of what we've done on the repository. You can find different notebooks in the repository. There's different notebooks for each of the steps Jesper mentioned. I'm going to focus very quickly on the first two, but mostly on this one, on module evaluation. In the dataset, in the notebooks, we're going to choose, we're going to use this data set, which is a sort of a toy data case. So the penguins data set, and it's a classification problem. We have some features, we want to classify the different class of penguins. In the first notebook, so data preparation, we're going to look at the data, doing some analysis of the feature. We can do that because we have a limited number of features, and afterwards we clean some data, we remove some none from the data sets, not particularly useful, and then we start our preparation by doing some feature pre-processing. The only takeaway message from this part is, remember that whenever you want to do any pre-processing, always remember train test split first, and then you apply the feature processing, as in you don't have to pre-process your test set. You have to apply the results of the processing or the training to the test set. That's a different thing, and that's to get ready to train our data. And in the evaluation, in the whole parts, we're gonna see examples of data splitting, then cross-validation. Stratification is one important aspect of data splitting. When you have different class distribution, when you're splitting in training and test, you want to keep the distribution of the classes in both the training and the test. So you want to retain the same class distribution. In other words, when you're sampling randomly, when you do the splitting, you're not sampling in the whole data set, but you're sampling in the class buckets. So this is better for future stability of the predictions. And this is sort of the case. So we have one class which is less represented. So if we just random split the data, we might end up not having any sample at all in the test set, which is not robust at all, because we want to evaluate in all the possible samples we have. But probably the most interesting bits for me is like this module evaluation bits. Yes,
we're running a little bit over, and we have a lot of questions for you.
Oh, brilliant. Okay, so I'll stop here and let's go with the questions. Or we can do late. We can do in the end, as you prefer. We could probably do in the end. I will keep track of them so I don't steal time to.
Valerio, I think it's nice if we do them now.
All right.
Because there is a lot of interest. So maybe let's just take them now, and we'll put short at the end of the workshop if we need.
Okay, fantastic.
The discussion as buffer, and like my closing is just saying thank you. So if Mike is okay with it, if it doesn't interfere. Okay, cool.
Cool. Brilliant. Right.
Do you
Shall I
want to
go?
finish your sentence? Because like it's I don't want to stop you.
No,
mid.
that's fine. That's very fine. I just want to say that if you look at the notebook, we had a quick joke about it, because since we're using a toy data set, I should have find a way in which I should broke it to prove the point I was trying to make. But in essence, in this choosing the property evaluation metric section in this notebook, what I did was choosing two classes, so the most represented and the least represented class. So we're just having two classes, again, binary classification to make it simple. Not because there's any limitation on the metrics, just to make it simple. And then I chose the features which was the most confusing one. So I looked at the different features we had and said, look, if we do classification choosing this feature, this two combination of features, so the flipper length and the Kuhlmann depth, this might be quite harder for a model to figure out which of the two classes might be. And so what I did was essentially proving the point that with this particular setting of the data, the same data just filtered a little bit, if you use in cross-validation and then evaluation, if we use the accuracy and the MCC, you end up with very different results. In accuracy, which again, remember, it just consider the good ones, so not the bad ones, as the MCC does. If you look at the accuracy in the average accuracy in cross-validation, you see 0.70, which seems reasonable. Actually, it's definitely not, because we're doing lots of errors on the negative here. And this is something we should spot in evaluating our model. So, yeah, that was the point. But you'll find the details in the notebook, so I'm more than happy to go through afterwards on Discord later today, not now. Let me have a look at the.
I think this leads over quite well to this question from ADE.
All right.
Are you implying that we should use a combination of F1 score and MCC metrics when validating our classification models?
No, what I'm implying is, according to my experience, MCC should always do the trick. MCC is quite reasonably good to catch all the performance you're looking for, but it really depends on the learning problem you have. If the classification, all the possible classes you have, considering classification problem, is relevant to you, certainly I wouldn't trust just accuracy. I wouldn't trust F1. I would definitely trust MCC.
Gemma, would you like to ask a question yourself? I think you actually had two, at least.
I'm muted. Okay, yes, I have two. One is more applied, Valerio. So when you are evaluating the model, I assume you're always using a cutoff of 0.5 to build these contingency tables, but I do know that when actually applying results, many people just take another cutoff as the truth, just because it works better on their problem, etc. So I don't know if you have any comment on that, or that's like something you should never do.
What do you mean by cutoff? Sorry.
So if you get a classification and the output you get is a probability, actually you take 0.5 as so.
No, well, essentially, depending on which metric you're using, if you consider accuracy, the accuracy is a metric which goes from 0 to 1. So essentially 0.5 means random classification. On the MCC, on the other hand, goes from -1 to 1. And so the random bit is on the 0. So MCC of 0 means random.
Yeah, sorry, no, I mean, you build the contingency matrix by putting each sample on one of the boxes. Right. But this is actually coming out of the model usually as a probability, not as a yes or no. It's actually the probability of active or inactive. Or whatever.
No, it's actually what the model is. Oh, yes. I mean, it depends on the model. It depends on the model. Yeah. So
you say that everything that is above 0.5, you put it in the active. So in the 1 and then, or
at some point, if I understood correctly what you mean, at some point you need to take a class. You don't want a probability distribution. If you're interested in the probability, that's a different thing. And yeah, so probably to your point, we're assuming hard classification problem. So every sample belongs to just one class. We're not considering a soft classification problem, which you have the probability of one sample to be multiple classes. So yes, at some point you cut off the prediction from the probability prediction from the model, and you say, okay, the model says this class.
Okay, thank you. And my second question was regarding when you cross-validate when you do cross-validation and then you have the different measures, do you simply do a mean plus a standard deviation to show the error? What is the most appropriate way of?
Amazing. I love that question. And that's very relevant. And this goes to the question I'm not actually answering in this slide, which is how do you interpret the results? So normally, long story short, you don't want to do standard deviation. You might lead to statistical errors. What you do want to do instead, it could be like you want to gather some statistics from cross-validation. So, for example, you might want to repeat the cross-validation multiple times. So you have, I don't know, let's say 50 samples in cross-validation. So 10 times 5-fold cross-validation, for example, that's repeated cross-validation. So you have 50 different runs of your model, and then you take you take the bootstrap confidence interval, so that you take the different results and see the confidence interval. Sorry. What's the confidence interval on your predictions? So how much you can trust, what's the boundaries in the confidence interval of your variation, which is slightly better than doing the standard deviation itself. Standard deviation is a good approximation anyway, but confidence interval is statistically more robust.
Shall we take the other questions at the end or via text? So we have Mike before the break. We're like running 10 minutes behind, so that should be like.
Yes, and
right,
I will try to answer the other questions in the chat in the meantime, in case.
Okay, cool. Otherwise, we have some for the end, which is great as well. Thank you so much for all the questions. And now it's over to Mike with some applied machine learning failures.